Hey kids, Smath here. I want to give you a little video introduction on types of chemical reactions. Most of us have already had this either in the summer course or during honors, but it's never bad to just touch on basics and then build upon it. So what I've got for you here is the 5 basic types of chemical reactions I want to talk to you about today. First one of these is called synthesis. Now, another word for synthesis you'll see in some books, it's called combination. All right. And as the name implies, we're always going to start out with 2 reactants that are going to synthesize, condense, combine into one product. So the key here for predicting synthesis reactions, they only have one product. Now, how do we know that it's synthesis? Can be a little more difficult. Sometimes we got to look at what we're starting with. And in this case, usually it's going to be an element and an element. If you see 2 elements sitting there, it's got to be synthesis. This is real easy. Just put those together. Now, the key with some of those elements is the non-metals tend to be diatomic, like chlorine. Our diatomics, remember, these always have to be accompanied by something or someone, or they will accompany themselves. They're found in pairs. These are what we refer to as our huckleberry fins, right? So you wouldn't find just Cl, you'll find Cl2 in nature, Br2, F2, I2. These are always going to be in pairs. These are the diatomics. Now, along with those, there are also 2 other molecular elements that we should be aware of. One of those is phosphorus, and phosphorus, you'll never see the word again, but just to introduce it, it's tetratomic. It comes as P4 instead of just P by itself. That's how phosphorus is found in nature if it's not an oxide, or how phosphorus, when it's pure, becomes P4. Then we have S8, another great word for you, octatomic. Okay, so P4 and S8 are 2 others. You should be aware of those. I don't think you really should see them very often in a synthesis reaction. That's kind of pushing the limits of this class. But here would be an example if you did see one. Other than that, it's just going to be the stuff like we did up top. Take a metal sodium, combine it with a diatomic, check your charges, make sure everybody's neutral, and you've got a nice synthesis reaction there. Now I'm going to go through decomp, and then I'm going to pull up another page. We're going to talk about a few special cases for synthesis and decomposition that we should be aware of, that the College Board likes to use, and just that we should know as good chemistry students. Decomposition is merely the opposite of synthesis. We're going to take one reactant, we're going to break it apart into 2 products. Super simple. This should be a compound that gets broken down into an element and another element. In this case, I have potassium fluoride. We're going to break it apart into potassium and fluorine. Watching out for our diatomic again. Fluorine is diatomic, so to balance it out, we have to put a 2 in front and a 2 in front. Those are decomposition reactions. Now I want to, like I said, add in a page here and talk to you a little bit about special cases for synthesis. So these are synthesis special cases. And there are 2 of these that we want to concern ourselves with. These are where we're not synthesizing elements, but that we're synthesizing compounds. And the compound we're synthesizing with is water, something so common but gets used a lot. And so in the first one of these, we're going to combine a non-metal oxide. So it's going to be something from the upper right-hand corner of the periodic table. Sulfur, nitrogen, phosphorus. Those are the very common ones. And we're going to combine those with water. And those kids are going to make an acid in generic terms. Here's a great example of one. We can take sulfur trioxide. Now that's a compound. That is not a sulfite ion. There is no charge up here. So this is a neutral molecular compound, and we're going to combine that with water and synthesize. Just add it up. Put the H out in front, and we're going to get H2SO4 out of this. Okay? This same thing can happen with, say, NO2. Combine it with a little bit of water. Nitrogen dioxide will end up making nitric acid. As I say, these are very common. Also be aware, the reverse of these, if you ever have to break apart an acid, break that acid apart, just rip some water out of it. This is like dehydration synthesis, okay? Rip the water out of the acid, make a little bit of, pull the water out, and then have a non-metallic oxide. All right, those are the non-metallics. Now, just like the opposite of a non-metal is a metal, if we take a metal oxide, we combine that with water, well, the opposite of an acid is a base. And we need to watch our bases here, because if it's a strong base, just like if it's a strong acid, it's going to dissociate. And that base is going to end up being split apart. Okay, so just like in this case, if we had H2SO4, we could dissociate that into H plus HSO4 minus. Okay, nitric acid, H plus NO3 minus. Same thing is going to happen with our bases, where if we take sodium oxide, Na2O, and we combine that with water, we're going to make NaOH. And if we balance this out, we're going to go 2, and everybody's going to be happy. But NaOH is a strong base. So let's break that apart. And a better answer is going to be Na plus OH minus. Okay? NaOH is a decent answer. Won't get you full credit. You have to dissociate strongs. All right? That's going to happen with any. I could do this with calcium oxide, CaO. Mix that together with a little bit of H2O. I'm going to get CaOH parentheses 2. Oh my gosh, that's one of the Catley bases. They're strong. Then I'm going to go calcium 2 plus OH minus, put 2 of those if we'd like to get it balanced. Now you're asking yourselves, what do we do if it's not strong? No problem. If it's not strong, like strontium oxide, well, that is still strong, sorry. We said beryllium and magnesium are not strong. Magnesium oxide in water. In that case, we're just going to leave it as a compound, MgOH2. Still soluble, it's still aqueous, but it's not going to dissociate as much. Same thing's going to go with your acids, but you're not going to find as many of those. Okay, so that's our metallic oxide, non-metallic oxide. Those are our special cases. Okay, now let's go back up to where we were in our notes with single replacement reactions. Single replacements are non-reversible. Everything else we've talked about has been a wee bit reversible. There are 2 kinds of these. There is a metallic version where we're going to have A and B that are both metals, and A is going to be more active than B on the activity series. This activity series should be in documents up in the top. Okay, this is going to tell us if the reaction will occur. A needs to be above B. And in this case, we have lithium, and lithium is going to take the case of A above iron B. Is Li above iron? Yes. This reaction continues. And the Li is going to boot the Fe away from the nitrate The iron is going to be left all alone by itself. So you have a metallic atom, an ionic metallic, an ionic metallic, and a metallic atom, a different metallic atom now. This is what metallic single replacements look like. And this reaction can't go backwards because when we try to run it backwards, running it here with iron, iron is not above lithium. Lithium's towards the very top of the activity series. And so we say NVR, and that stands for no visible reaction. You may also see some books that just say NR, no reaction. Be familiar with both of those. So that's how metallic singles work. We can also have replacements with halogens. A halogen can replace itself. So in this case, we're using D as a halogen and G as a halogen, okay? And the D is going to replace the G to make ED and leave G by itself. Just remember that these halogens tend to be, these are all diatomic. So the halogen doesn't really have an activity series. It follows the activity that's on the periodic table, with F being most reactive and I being least reactive there. Okay, I think I've got an example for one down here where we say fluorine is going to try to replace iodine, and that can happen. Fluorine's at the top, so the fluorine comes in, boots out the iodine. We now have iodine by itself, and potassium fluoride is left over. Okay, these also can't run backwards. These are still single replacements. They're non-reversible. So if we try to get bromine to replace chlorine, well, sorry, that can't work. Chlorine is in period 2, bromine's in period 3. Not going to happen. Great place to use that NVR again. Not a visible reaction is occurring. So what's going to happen if you take some sodium chloride and you pour some bromine liquid into it? Nothing. The bromine's probably more dense. It's going to sink to the bottom and just sit there in a layer of brown liquid. Bromine's brown. Okay, so those are single replacements, and we need the activity series for metals, or we need the periodic table for halogens. Okay, and then double replacement. We have 3 down, 2 to go. Double replacements, this is where everybody switches partners. Okay, kind of like a square dance. Mix the first A with D and B with C. And for these are always going to be 2 ionic species. So these are not going to occur with molecular species or nonmetals. These are always going to be ionic things. They can be polyatomic things, but the lead is going to combine with the iodine here and form lead iodide, and the potassium will form with the nitrate and make potassium nitrate. Okay, the charges of your metals will stay the same in these. They will not change. That's a different kind of reaction that's going to happen later on in this chapter. For these, we're going to look at solubility rules to see what's going to happen. Now, we're going to try to simplify. Soluble, marginally soluble. These are terms you may see. Marginally soluble means it's going into solution. And then slightly soluble and insoluble do not go into solution. So think of it that way. Soluble and marginally soluble are we're going to treat together. Slightly soluble is not soluble. And these means they don't. We're going to put them in there. It's just going to sink down to the bottom, or it may float on top. It's just going to sit there. Solubility rules 1 through 6. Know them. Know how to apply them. Come see me and ask me questions if you don't know how to use these. That includes knowing these exceptions. They show up on the board all the time. Okay, and I've been very clear in here in using the terms soluble as much as I could. I had to use the words marginally a couple of times with these three. But other than that, know what's soluble. If there isn't a rule that applies, then you're home free. You're not going to see it on an evaluation. Okay, but you do need to know and memorize these. There's a simplified version of these. Okay, I would say let's take that, put a big red box around it, give it a couple asterisks, and say, hey, you should memorize these. You guys mastered those pi-atomics. You can memorize 5 simple rules. Okay? Last kind of reaction is a combustion reaction. And so for combustion reaction, we've got hydrocarbons, C's, H's, and O's, a little bit of oxygen maybe, combining with a hydrocarbon. All right, those are our hydrocarbons, excuse me. And then we're going to combine that with a little bit of oxygen. If it uses the term complete combustion, that means you're making CO2. Okay? If it's an incomplete combustion, you may see CO. They're relatively uncommon, but I want to at least say I've shown them to you. They will usually say a hydrocarbon consisting of carbon and hydrogen is completely combusted in excess oxygen. So they will tell you it's a complete. If they don't tell you, assume it is a complete combustion. Don't assume incompletes. All right? So the simplest of these, methane gas, CH4. Easiest thing we got. Combine it with oxygen, you get CO2 and H2O. These are so great to predict. They always yield CO2 and H2O. We love that. Okay, then we got a balance. We got 4 hydrogens, so put a 2 out front. That gives us 2 oxygens there and 2 oxygens there, so we put a 2 out in front of the oxygen to get them balanced. Okay, butane, a little Bic lighter, butane lighter, okay? C4H10. If you go through and do this with an even number of carbons, we put a 4. Normally, we would say, hey, why don't we put a 4 out in front of the CO2 and I'll put a 5 out in front of the H2O. Well, if I do that, I'm going to have 13 oxygen. Now, we're good, but we can't get 13 oxygen from something that comes in a pair. And so what you have to do is go back to the beginning. And in that case, you're going to put a 2 out in front, make the 4 into an 8, make the 5 into a 10. And now, instead of 13 oxygen, we need 26 oxygen. That's much easier to do. And put a 13, and put a 13 out in front of our oxygen. So if you have an even number of carbons, look for that double. It may happen pretty commonly. Okay? And then there's also elemental combustion. Elemental combustion is where we take an element and we simply combine it with oxygen to make an oxide. If it's a transition metal, pick any charge you want. Pick 2. Transition metals oxidize with a +2 oxidation state. That's pretty safe almost all the time. Okay? Let's put it together now. I've been going for about 20 minutes. Let's put it together. So we have side notes. Burning, what does that mean? It means we stuck something directly into a flame and it combined with oxygen. Heating, what does that mean? That means I put it in a test tube, or I put it in a crucible, or I put it in an evaporating dish and I heated it, maybe with a flame, maybe with a hot plate. Burning implies that we're adding, and adding implies that it's going to probably be synthesis or it's going to be combustion. Heating means breaking things apart. That's decomposition. Okay? So those 2 things are good. And then I have a page of takeaways for you here. Okay? And for these, I've got carbonates. our decomposition. Okay. I have a couple of decompositions that I want to show you, and this is one of them, where you take a carbonate, and this is going to break apart and form H2O and CO2. Okay. That happens all the time with carbonic acid. It's one of the ways that they get carbonation into soda is they pump CO2, but they also put carbonic acid in, and that carbonic acid breaks apart into H2O, and then it gives you the bubbles. That's what keeps the soda fresh over time. So there's one that you must break apart if you get H2CO3. When you have it as a product, please break it apart, decompose that. Another one is ammonium hydroxide. That will instantaneously decompose into ammonia and water, and H3 and H2O. Okay. Other takeaways, only aqueous things split. Solids, liquids, and gases do not split apart. So when we're doing net ionic equations, only split ionic aqueous things. Please. H2O is a liquid, except when we combust it. If we combust it, it's going to be a gas. It's going to be running at a pretty high temperature, a couple hundred degrees. So that's going to be a gas. Okay. Other takeaways, if you have a solid and combine it with a gas, you will continue to have a solid. That's common sense. Solid and a gas are going to make a solid. They're not going to make an aqueous thing. There's no water in this to make anything aqueous. To make something aqueous, we have to have water, or we have to have an aqueous thing to start out with. Okay? Then H2SO4, if you noticed when I did that acid, that non-metallic oxide, and I made sulfuric acid, I only split it apart one H at a time. First H comes off real easy. Second H, not so much. It's a lot harder to break that second H off of there. So that's how that splits apart. Got about 5 more of these. If you have a double replacement, all right, and it ends up being the same when you try to double replace it, then it's probably a synthesis. You're going to run into one of those. All right, you'll see. It's going to be with water, and it's going to be an oxide. Go back and look at our metallic and non-metallic oxides. If you try to run that as a double replacement, you're going to end up with oxides again. You can't do that. Okay, so then look for it to be a synthesis. H plus is equal to H3O plus. They're synonymous. It's just one has water with it, the other one does not. Acids and water make H3O plus and an anion. Okay, and then these last 2 takeaways are the ones that I already just gave you. Okay, so those are our takeaways, and those are our 5 basic types of reactions. I'm going to call this video out here, post it for you guys, and then I'm going to come in and we may do this next set of examples on video for you to look at as well, because with reactions, as with most chemistry, the more problems we do, the more familiar they look and the better off we are. So I'm Smath, and these are 5 basic types of chemical reactions, and I hope this video helped you.